Hello everyone, in this video we will be covering chapter 17. The main point of this video is Brownian motion, and specifically the standard Brownian motion is actually called the Wiener process. So the Wiener process is pretty much just a standard Brownian motion. All the properties here apply to any Brownian motion, but you should think of the Wiener process as like the standard normal distribution and Brownian motion like the general normal distribution. So the Wiener process, which I'm just going to call Brownian motion from now on, has the following the following properties. The first one is the W of 0 is equals to 0. And then for any partition, so if you cut the time from 0 to Tn, then each increment, which will be from here to here, this will be the first one, then from here to here and so forth, they are independent. This is very, very important because that means this increment is independent of this one, this is independent of this one, and so forth. Actually, WTI minus WT0 is also independent of WT0. The third property is the following: the increments for any s less than t have a actual normal distribution. In this case, this is a standard normal. This is why this is called the Wiener process. So this is a standard normal distribution where the expected value of the variable is 0 and the variance is t minus s. And technically this should be sigma squared, but since this is a standard, sigma is equals to 1. That's why this is only equals to t minus s. So in other words, remember this technically means that wt minus ws is a normal distribution with mean 0 and variance t minus s. Or probabilistically speaking, and again this is not new, the probability that A is less than Wt minus Ws, then this is less than B. This is equals to the integral 1 over 2t minus s, then 0 to actually a to b of e to the minus c squared over 2t minus s, the whole t in dz, which is just the area between a and b. All right. And Brownian motion is going to be a very important process, so you're going to see this process pretty much until the end of the class from now on. Brownian motion has the following properties, and we are specifically talking about here about the Wiener process, but this expands to any Brownian motion. The first property is this: the expected value of Wt is equals to 0, and the expected value of Wt squared, or the second moment, is equals to t. The trajectories of Wt are continuous everywhere. So this is something that is very important, which is possibly something you have never seen before. So the trajectories are continuous, but they are not differentiable anywhere. So the graph of the paths of Brownian motion look like this, which clearly you can tell that they are continuous. So you can see the paths are continuous, but they are not differentiable anywhere, which means the derivative doesn't exist anywhere. There is a fourth property which we're not gonna get into much right now. I'll just mention it, and once we need it, we'll look into in more detail the four properties called the quadratic variation. And the quadratic variation is defined as follows. Epsilon of h is defined to be the sum from k equals to 0 to n minus 1 of w tk plus 1 minus w tk, the whole thing square. Notice that this is just the sum of the increments square. That's why it's called quadratic variation. Okay, let's see why these properties are true. So let's look to number 1. So we want to show that the expected value. So we want to show that the expected value of Wt is equals to 0. Okay. So notice that Wt is the same thing as Wt minus W0. Why? Because remember W0 is equals to 0. But by the definition, this is a normal distribution with mean 0 and variance t. So therefore, this implies that the expected value of Wt is the same thing as the expected value of Wt minus W0. But since this is a normal distribution where the expected value is 0, well, this is just equals to 0. Now, number 2, notice that the variance of Wt by definition should be equals to the expected value of Wt squared square minus the expected value of Wt square. So this is the definition of variance. But we just show that this part was equals to 0 from part 1. So therefore that implies that the expected value of Wt squared is the same thing as just the variance of Wt. But since Wt is a normal distribution with mean 0 and variance t, therefore that means the expected value of Wt squared is just equals to t. Now, to show that the function is not differentiable is either very easy to see, but it's actually pretty complicated to show. But let me just give you an illustration of why it doesn't exist. So let's define nu h of t to be the difference of two Wiener processes, or the difference constant that you saw in calculus 1. Right, so clearly you can see that this is a normal distribution with mean 0 and variance 1 over h. Now, if we wanted to find the derivative, in theory, the derivative of this, okay, is equals to the limit as h goes to 0 over this part. However, this is the definition for non-random functions, so this doesn't apply when the functions are, or the processes are random. So therefore this definition doesn't make sense. So that's why the derivative doesn't exist anywhere. So that means it's not differentiable at any point. The proper name is to say that it's not differentiable almost everywhere, which means that the probability that will be differentiable somewhere is equals to 0. Again, the function is continuous, it's not differentiable, so one more time, you will want to do a graph. Remember, the graph starts in 0, and the path will look like this, which you can see clearly is continuous because you can draw it without lifting the pen, but the function is not differentiable at any given point. All right, now let's do a couple examples to see how Brownian motion behaves. So here is the first question. What is the distribution of Wt plus Ws where S is less than T? Well, we already know, okay, so we already know that Wt minus Ws is normal 0 T minus S. But that doesn't mean that these two are the same, okay? So you have to go back to what you know, which is this. So the first thing we had to do is rewrite this in a more convenient way, so we can use something like this. So therefore, one way could be this. Wt, then it will be plus Ws, and then you add and subtract Ws, which is one of the most common tricks in math, which is to add 0. So you add 0 to this, you end up with the same thing. Then we rearrange it. So you combine these two, you end up with you combine these two, it will give you 2 Ws, and then you combine these two, it will be plus Wt minus Ws. Remember, all of this is true for S less than or equals to T. Now, from a probability class or statistics class you have taken before, you should remember that anytime that you combine normal distributions, the distribution has to be normal. The only thing that changes is the mean and the variance, or the standard deviation. So that's what we're trying to find in here. So from the previous page, we know the following. So we already know this, that the expected value of Wt minus Ws is equals to 0, and also that the variance of Wt minus Ws is equals to T minus S. Okay, so we already know that. We also know the expected value of 2Ws is the same thing as 2 times the expected value of Ws, which we also know is equals to 0. And the variance of 2Ws is equals to 2 squared the variance of Ws, which from the previous page, this is equals to 4 times S. So that implies the Wt plus Ws has to have a normal distribution where the mean, if you add 0 plus 0, you still get 0. And then if you add the variances, so this will be 2 t minus s plus 4s. That should give you 3s plus t. And that's it. Here, remember, we use the property, the variance of k of some random variable x is equals to k squared the variance of x. Right, let's do another very similar example. So this is pretty much asking the same thing, Exactly, and now it's specifically saying the mean and the variance, and we already know this is going to have some kind of normal distribution. Right, so clearly here S is 1 and T is 4, so this is T is an S. So we're going to do a very similar trick like the one we did in the last example. So this is what we have, 4W4 plus W1. This is equals to 4W4. Then we're going to add nothing to it. So you subtract minus 4W1. Then we add 4W1. And then we already have W1 in here. Right, so here you can factor the 4. So this is 4W4 minus W1. And then if you combine these two, this is 5W1. Again, if we use the results from the previous 2 pages, or from the previous example 2, we know that the expected value of 4W4 plus W1 has to equals to 4, the expected value, W4 minus W1 plus 5, the expected value of W1. Now remember that this has a normal distribution with mean 0, so it will be 0, and therefore this one is also 0. So the answer to the expected value is 0. Alright, what about the variance? So the variance of 4W4 plus W1 is the same thing as 4 squared, the variance of W4 minus W1 plus 25, or 5 squared, the variance of W1. This will be 16 times 3. Why do we get 3? Because remember, this is a normal distribution that has a variance of 4 minus 1, which is 3. And the second one has a variance of 1. Once you simplify everything, this gives you 73. Again, as you can see, the key is to write this so that it matches the definition of the Wiener process or the gradient motion, and then just apply the formula and you can get any of these answers. This, by the way, is actually one of the homework problems, but in the answer, in the back of the book, they only tell you that this is equals to 0 and this is 73. Okay, now we're going to talk about martingales in continuous time. We did a lot of martingales in discrete time, and since you love them so much, we're going to do them again in here. The definition is very, very similar, except that now we are in continuous time, but you still have to check 2 properties. So MT, which is a random process, will be or a continuous random process, is a martingale if the expected value of the absolute value of the process is finite, which was the same as before, and if the expected value of N of T given the previous information is equals to M of S. M of U goes up to S. Again, this is exactly the same idea as the discrete time. Now, just to refresh your memory on the discrete time, usually we have this expected value of xn given an minus 1, and this was equals to the expected value, this was equals to x of n minus 1. Remember that this is the information up to time n, so up to time n minus 1 for the discrete time, and this was an algebra. In continuous time we have algebras too. They are called sigma algebras, so therefore you can also rewrite this as this. This is going to be f of s, and this will give you m of s. The only thing you have to worry about this part is that this is the information up to time s, and this is called a sigma algebra instead of algebra. But for the purpose of the remaining of the class, or at least for this section, all you need to know is that this is just the information up to time s. All right, so let's do a example now, and the example is actually very interesting because of this. The example is the following. So show that the standard Brownian motion Wt for t greater equals to 0, so this is the Wiener process or standard Brownian motion, that this is actually a martingale. So that's what we're gonna show. All right, so the first part, well, the expected value of the absolute value of Wt, this should be obvious that it is finite. Why? All right, so this is gonna be left to the reader to check. It's actually pretty easy to show this is the case. Remember that the expected value of Wt with the absolute value is equals to 0. So you put the absolute value there, things shouldn't change that much. So you should check this yourselves. It's actually pretty easy. Now what about the second property? All right, so we want to show the expected value of Wt given the information or some sigma algebra up to time s, that this should equals to Ws. So this is what we want to show. Okay. Now we're going to use the same trick again, and remember that if we have Wt, you can rewrite it as Wt minus Ws plus Ws. Here the increments, which will be this and this, are independent, so Wt minus Ws is independent, so this is the symbol for independent from Ws. So this is going to be the key to showing there is a martingale. So therefore from here, that means that the expected value of Wt given the information up to time s is the same thing as the expected value of Wt minus Ws given the information up to time s plus expected value of Ws given the sigma algebra f of s. However, here, this is the part to be careful. Remember, this is independent of this part, which means that this is independent of the information up to time s. And from the rules of expected values that we did before, since these two are independent, so therefore this is just the expected value of Wt minus Ws. And here, since this is measurable with respect to s, which means you already know this by time s, then this is just equals to W of S. This is using the same properties that we did before. Remember, this means measurable. That's why this is the case. You only get that. And here it is because they are independent. But we already know that this part is equals to 0. So therefore, the only thing left is WS. So this is equals to WS. And this shows that this is a martingale by definition. Okay? Remember, if we were trying to show this, that's exactly what we got. This gives you this. Okay, let's do another example. So you didn't get the last one. This is a chance to redeem your sins. So we're gonna show that this process is a martingale. So this is what we have. Let xt be a Brownian motion. Notice that this is not the standard Brownian motion anymore. This actually should be sigma square. You can write sigma also. You just have to be careful that you know that if you really write sigma, this is the standard deviation, and you write like this, this is the variance. You have to be careful that you know which one is which. And we want to show that this is a martingale. We actually did the same problem in discrete time. You may even have this one in the last test, but we have done this example in discrete time. So now we're going to do it in continuous time. All right, so we can do the problem straight from here, or we can define a new variable. So let's say that bt is equals to xt squared minus sigma squared t. And what we want to show is this, that the expected value of bt in absolute value is finite. Again, this is kind of obvious, but you should still check. So you should check it. Remember that this is a normal distribution, so therefore the expected value we already know is finite. So number 1 is fine. Number 2 is the one that requires all the work. So here we want to show that the expected value of bt given f of s, that this will be equals to b of s. So this is what we want to show, that is equals to this, where remember that this is equals to x of s squared minus sigma square of s. So that's what you want to show. So let's start at the beginning. So therefore the expected value of v of t given the sigma algebra or the information, this is the same thing as the expected value of xt squared minus sigma t squared given f of s. Okay, so notice the x of t squared is the same thing as x of t minus x of s plus x of s. So this is the same trick we did before, square. Now let's say that this is a and this is b. Remember from basic algebra, you have a plus b squared. This is equals to a squared plus 2ab plus b squared. So therefore this gives us xt minus xs squared plus 2xs times xt minus xs, and then plus xs squared. Notice that this part is not random, so you can leave it alone for now. Just don't forget that it's there. Okay, so therefore from here we got the following. This is equals to the expected value of xt minus xs 14 square given f of s plus twice the expected value of x of s times x of t minus x of s given f of s plus expected value of x of s squared given s of s, and then minus sigma squared t. Okay, remember, do not forget about this part, which is this one. All right, remember that this was independent of this because of the independent increments that we talked about before. So therefore, the first part is just going to be the expected value of xt minus xs. Now, for the second part, this is independent of this, or actually this is measurable with respect to this, so you can take it outside, just like we did before. So this will be 2 x of s times the expected value of x of t minus x of s, which this part is also independent of this part. So this should be the expected value t, and then clearly this is measurable with respect to this. Hence, for the third term, or for this part, you only get x s squared, again because this is measurable with respect to this, and the second part just goes here. Now remember the x of t minus s, so remember that xt minus xs is a normal distribution with mean 0 and variance sigma square t minus s. So therefore from here this will be equals to sigma square t minus s. Remember that it expected value of a variance, or expected value of a variable is 0, then the expected value of x squared is the same thing as the variance of x. Now here I'm missing the square. Also remember that from the same reasoning from here, this part is equals to 0, so all of this is gone. So this will equal to sigma squared t minus s plus x of s squared minus sigma squared t. You break this into two pieces, you end up with this, where clearly this and this cancel. So the only thing you have left is x of t squared minus sigma s, which is just b of s, and that's what we wanted to show, and that's it.